Now I'm going to talk about load lines, and so first we're going to look at a magnetic circuit that just has an air gap, and then we'll add and a magnet, and then we'll add some winding to the problem too. So the objective here is to relate the magnetic field in a device to the magnet BH curve. So if you have a device, the magnet must be operating at a particular point on the BH curve. What is that point? So if we look at this magnetic circuit, it has some gap, LG, and then this circuit here has some magnetic steel which had some relative permeability, μs, and then in this hashed region there's a magnet material, and that has a length Lm, and then the path around the magnetic circuit, and we'll assume it's the center path, that has a path length of Ls. So this is Ls. Okay. And we'll assume here, assume no leakage or fringing, which is reasonable as long as the air gap length is small. So now from Ampere's law, we have, H dl equals Ni. Now in this magnetic circuit we don't have any Ni, any current. So the right side of this is 0. So then instead we have Hm Lm, magnetic field intensity, times the length here, that's the Lm, plus 2 times Hs Ls, that's in the magnetic steel, plus Hg Lg. Lg is the length of the air gap, and that has to equal 0. So I'll call that equation 8. And then in addition to this Ampere's law, the magnetic circuit has to satisfy the flux flowing through the circuit, because we're assuming no leakage and no fringing. And so therefore we would have that the Bm Am, now I didn't draw it on here, but you could picture the magnet having some magnetization direction. So that the magnetic flux density due to the magnet times the area of the magnet has to equal the field magnetic flux density going through the air gap times the area of the air gap, and that also has to equal the magnetic flux density going through the steel times the area of the steel. Okay. Now I want to play around with this so we get the relationship between the the magnetization flux density Bm and the magnetization field intensity Hm. Okay, and then we'll see what that gives us. So so from 9 we can rearrange. So we know that B is equal to mu h. And so then from 9 we can rearrange it and write that Hg, if we put the Ag on the denominator, we've got Hg is equal to Bm Am divided by mu naught Hg. Okay, because Hg times mu naught is B. And then we also know that the magnetic field intensity in the steel can be written in terms of the magnetic flux density in the magnet material. So we can write Bm Am divided by mu s As, like that. Okay, so we have these two relationships where the right side has Bm in it. Okay, now we can also rearrange equation 8 so we express it in terms of Hm. So rearrange 8. Hm is equal to minus Lg Hg divided by Lm minus 2 Ls divided by Lm Hs, and I'll call that equation 12. So I just rearranged 8. Now looking at that, we can now substitute in 10 and 11 into 12, and that will then eliminate Hg and Hs. So let's do that. So 10, 11 into 12 gives Hm is equal to minus Lg. Now I'm going to substitute it in, and I'm going to take the Bm out and put it on the outside. So we'll have just geometric and material properties in the square brackets. So we're going to have Lg Am divided by mu naught Lm Ag plus 2 times Ls Am divided by mu s Lm As, like that. And that's all times by Bm. Okay, so that's nice. So now we've got the magnetic field intensity related to the magnetic flux density for this device. And so this is all of the parameters that can affect the operating point of the magnet. So if we could therefore plot it, right? We could plot how Bm changes with Hm. So this equation is called the operating line, sometimes called the shear line or the load line. Now if mu s is much greater than mu naught, so the relative permeability of the steel is much greater than air, right? So this is mu naught times mu r in this mu s. So if mu s is much greater than mu naught, then this second term here can be approximated to be 0, will be small. So let's just do that. So if mu s is much greater than mu naught, we can approximate 13 to be Hm is equal to minus Lg Am divided by mu naught Lm Ag Bm, or Bm is equal to minus Hm mu naught Lm Ag divided by Lg Am. That's equation 14. So here Bm is on the y-axis and Hm is on the x-axis, so we could plot that. So it's a negative on here. So if it's a negative on here, then if Hm is negative, then it will become a positive magnetic flux density. So we have the BH curve for the magnet material, where this is HC, and so this is a linear BH curve, because we've chosen the material so that it's nice and linear. And then we have so that's the so we have Bm is equal to mu naught mu RH plus Br. That's the first curve. And then we have the load line, this load line curve, where now we apply a negative Hm. So then we would have a line that goes up like that, and the point where, so this would be the load line. I'm going to call it load line, aka operating line. So where the load line intersects the BH curve line for the magnet material is the operating point. Of the magnet material. If we had if we look at this, we can note a few things. Let me write something here. The intersection of the load line with the demagnetization curve this is the demagnetization curve or line yields the operating point. So depending on the air gap, we're going to have a different operating point. So yeah, right. So if I was looking at this one. If we look here, we've got LG on the denominator. So if LG was small, then the gradient would be large, right? And so then the load line may be like this. And so, which makes sense, right? Because then we would have a higher magnetic flux density in the air gap, because the reluctance has gone down in the air gap. And so we have a higher magnetic flux density. So this might, so now the ultimate would be if we go back to this one here, if we made LG equal to 0, then we'd only have this term left, right? And that would be due to the reluctance in the magnetic steel. So this, you could think of this point as maybe being the short circuit point for the magnetic circuit if we closed this air gap. We're not going to be at the complete top. There's still going to be some drop because of the reluctance in the steel, but we'd be pretty high up there. So this could be, considered the short circuit. Again, it's a magnetic circuit, so a short circuit. So the LG goes to 0. Whereas if our load line was down here, that could be considered having almost like an open circuit. The air gap was really large. Large LG. Can we cannot dynamically change the operating point though, right? Because there's no excitation. So it's kind of not so interesting because we don't have any current excitation in here. Okay, so if we just go back and take a look at this magnetic circuit again with the magnet present only, it's important to note that we can actually make the magnet look like a model as a reluctance terms. If you recall from previous class, you could model a magnetic circuit using reluctances. So how do you represent a magnet with reluctances? So if you go back and look at the load line equation that we got before, we have this here. So now also we have that the magnet material has BH properties like this, where if it's a linear, for the linear case, where we have BR here and HM is sorry, no, this is BM HM, and then we'd have a load line like this. So the load line is described by the first equation, and the magnet property line is explained by the second equation. So now, with these two, we can substitute them in, and if we do that, we substitute the first equation into the second. So if we do that, we get Bm is equal to minus Bm, mu naughts cancel, mu r, am, ag, lg, lm plus br. So in here we've got the mu r as well, you see. Now, so this is in terms of this is in terms of magnetic flux density, Br and Bm. Now we could convert this into flux by multiplying by the area. So let's do that. So multiply both sides by Am, and then we get then we can define flux M is equal to Bm Am, and flux R is equal to Br Am, where this is the magnetic flux density residual value. So then, using this definition here, where we've multiplied both sides by Am, we can then write that flux M is equal to minus flux M mu R Am Ag times Lg Lm plus flux sub R. Okay. Now, looking at this a little bit, we could further rearrange it, so moving things around, so we can put the mu R inside of here, and we'll multiply the top and bottom by mu naught. So we have mu R, mu naught, Am divided by Lm. So this is all in terms of magnet material properties, and then Lg divided by Ag mu naught, that's in terms of air gap properties, plus the phi r. Now we should be able to see what these two terms are. They're reluctance terms. So Rm we could define as the reluctance of the magnet material, which is Lm mu naught mu r Am, and Rg is equal to Lg mu naught Ag. So this is a new term, magnet reluctance, and we've seen this before. This is air gap reluctance. Okay, so now substituting these reluctance terms in, we get that the flux M is equal to minus Rg over Rm, right, times flux M minus flux R. Now if we rearrange this a little bit, so we put all the flux M's on one side, we have 1 plus Rg Rm is equal to wait, this should be a plus here, sorry, make sure you put that as a plus. It's equal to phi r, and then if we rearrange this then we'll a bit more, we can write that flux M is equal to flux R Rm over Rm plus Rg. Now what does this look like? Remember from electric circuits, this is like current division. So equivalent to current division. So we can draw that, how that looks. So if we have some flux R coming in, then what this would mean is we have two reluctance terms, right? And this would be Rg, and this would be Rm, and the flux M going through the air gap is going to be the division between the magnet reluctance and the air gap reluctance. Okay. So then if we go back now to looking at our magnetic circuit here, right? If we see a magnet then, and we're modeling the magnetic circuit with the magnet, and we want to change that into a reluctance term, we could take this part and replace it with the magnet reluctance term and a source, flux source term, which would be equal to Br times the cross-sectional area of the magnet, like so. Where this would be the air gap flux. So here this flux M is the air gap flux. Does that make sense? So you can now, with this equivalent circuit approach, you can model the magnet material by replacing it with these two terms. So that's quite useful when trying to model magnets. Okay.